Okay, so I hope the screen is visible to everyone. So in the previous class, we have gone with the basic construction of MOSFETs. So there we have seen there are two different type of MOSFETs, enhancement and depletion type. So in case of enhancement type, we are having like there is no channel formed, and in case of depletion type, there will be a predefined channel will be available between the source and drain. Okay, so this is your depletion type MOSFET, and this is the enhancement type MOSFET, EMOS or DMOS. Okay, so here in case of depletion type MOSFET, it is if it is N channel, there will be a channel formed that is basically of N type, or here in the channel region there will be an electron, high concentration of electrons will be there in case of N channel depletion type MOSFET. So there will be drain and source and a gate. Okay, so this gate will be of metal or a polysilicon. Okay, metal or polysilicon is there, and in between there will be an SiO2 layer. So this is metal oxide and semiconductor. So this is your metal, this is oxide, and this is your semiconductor. This is MOS device. So this will be the structure in case of either depletion type or enhancement type. The only difference is there will be a channel formed. So this is a predefined channel. So this is predefined channel, and if it is of N type or N channel is there, so the channel will be of N type, like most of the electrons will be there in the channel will be formed because of the high concentration of electrons in this source and drain region. Okay, if it is a P channel depletion type MOSFET, there will be a predefined channel, and this channel will be formed by because of the holes availability, because large number of holes will be there in this region between drain and source. So this will be forming because of the holes. Okay, so this is your P channel depletion type MOSFET. Okay, so next one, if it is enhancement type, so in enhancement type the similar structure will be there. The only difference will be there in construction wise is there will be no predefined channel. So between drain and source there is no channel. Here no predefined channel. Okay, so there is no predefined channel, and the channel will be formed only when we are applying some voltage. So gate to source voltage we are applying. If we are applying gate to source voltage, that is if it is of suppose this is P substrate is there, so channel will be form of N channel. N channel will be there, like NMOS is there or N channel. So if it is N channel, we need to form a channel. So to form this channel, we need to apply a positive gate voltage so that electrons will be collecting near this oxide region. Okay, in the substrate itself, near this oxide there will be accumulation of electrons will be there. So this accumulation will be with respect to the applied VGG or gate to source voltage. Whatever gate to source voltage we are applying, if we are applying, there will be increase in the electrons near this oxide region. So that will be inducing a channel. Okay, so here in case of N channel, that is of enhancement type, we are going to induce a channel based on the applied gate to source voltage. So basically here there will be no predefined channel, but channel will be induced by applying the gate voltage. Channel is induced. Okay, so next we will see the symbol. So in case of depletion type MOSFETs, we are having the symbol is there will be, first of all there are four terminals are there here. So gate, drain, source, and another terminal that is this one. This is called substrate or body. So substrate or body will be there if it is N channel. So the substrate will be connected to this a source. Okay, and it will be uh, pointing like the arrow direction will be inside. Okay, so if it is P channel, the substrate is like here again connected to source, it is drain and gate. So this is the symbol in case of depletion type MOSFET. So in case of enhancement type MOSFET, the symbol will be given by this symbol of enhancement MOSFET. So here gate, source, drain. So gate is drain and source again, and there will be another body terminal. The body terminal is connected to source. Okay, the arrow direction will be again similar to this one also. Arrow direction will be there. So the only difference is there is a continuous line at the gate side, but in case of enhancement type there will be a discrete line. Okay, so this discrete line indicates it is not having a predefined channel. So if it is having a predefined channel, the line will be continuous. If the line is not continuous at the gate side, it will be like discrete, showing a discrete nature. So that means there is no predefined channel. So it is showing like there is no predefined channel. So this is the symbol of enhancement type MOSFET. I hope you have got. So the next we will see is the operation of enhancement and depletion type MOSFETs. Okay, so we will start with the operation of depletion type MOSFETs. Operation of DMOS, like depletion MOSFET. So we have seen the construction. So in construction wise, it will be having a predefined channel. Okay, so if it is having predefined channel, the structure we can just draw here. This will be a substrate on which we will be having two highly doped regions. That will be like, if it is substrate is of p type. Okay, so this is p type substrate. On p type substrate, n channel is formed basically. Okay, so if it is p type substrate, this will be n plus and n plus, and this will be giving out the oxide, and here we will be having metal for the connection. So this is gate terminal, and here also the metal will be there. That will be drain. This will be source, and in this region there will be predefined channel. So if it is predefined channel, there will be a predefined channel between source and drain. Okay, so by construction wise, this will be the structure. But if we are going to see the operation, like how it is going to operate, so we need to bias this depletion MOSFET such that the gate to source voltage should be reverse bias. Okay, so this is the main motive in case of depletion type MOSFET. So depletion type MOSFET is, we need to, if it is depletion type and it is going to operate in depletion mode. So a depletion type MOSFET can operate in either depletion mode or it can operate in enhancement mode. We will see both depletion mode operation and enhancement mode operation. So for depletion mode operation, what we need to do is, so suppose if it is n channel MOSFET is there, n channel depletion MOSFET. Okay, if it is n channel depletion MOSFET, so if we need to operate it in depletion mode, then we will be applying gate to source voltage. Gate to source voltage should be less than or equals to 0. That means we need to apply the gate to source voltage in negative direction. That means either we should be making gate to source voltage equals to 0, or we'll be making gate to source voltage in the negative direction. But the same n channel DMOS is going to operate in enhancement mode. Then we will be applying gate to source voltage. We need to apply gate to source voltage either equals to 0 or greater than 0. Okay, so this is the basic difference between enhancement mode and depletion mode operation. In depletion mode, for n channel MOSFET, we need to apply gate to source voltage less than 0 or equals to 0, or in case of enhancement type MOSFET, we will be applying gate to source voltage equals to 0 or greater than 0. So we will start with the depletion mode operation. So first case like depletion mode operation. So in case of depletion mode operation, the biasing will be such that we are going to have the gate to source voltage in negative direction. So just we can see okay, so this is your gate. So gate should be biased such that we should be biasing it with a negative voltage. So it is biased with a negative voltage. Okay, and it should be connected to the source terminal. So this is source, this is gate, and this is drain. So this gate to source voltage should be negative, and it will be a variable, like we will be varying the gate to source voltage, and drain to source voltage at that time will be biased, like it should be biased such that the drain to source voltage should be a positive value. Okay, and here also we will be having a, like in operation case, we will be varying the drain to source voltage also, and gate to source voltage also, and in between we will be connecting a resistor. So at the output, like at the drain direction, we will be having a resistor. Okay, so that is RD. So this is the structure, or in terms of symbol, we can just write, if it is symbolic representation, we will be just representing like, so this is the there, it is of n channel. Okay, so if it is n channel means we will be connecting it with a resistor in positive. This is source, this is drain, this is gate, and the gate will be reverse bias, so it will be biased with this. Okay, so this is the biasing, and the substrate or body bias, body terminal, we can neglect it, or we can just make it to this. Okay, positive, negative. So this is basically the negative and positive. So this is VDD, we can call it, and this is VGG voltage. Okay, so here we are going to apply, this is negative and this is positive, this is VGS, and this is positive and this is negative, this is VDS. Okay, the voltage across this. Okay, so this is the basic structure in case of depletion mode operation. This is the structure we need to implement. This is RD, that is output resistance. So here basically with respect to applying gate to source voltage, we need to consider the current flow. Okay, so here this is current flow we need to find out. So if this is a positive, Okay, and this is n-type side, so that means this is source and this is drain. So electrons movement will be taking place between, like the electrons will be moving from source to drain side. That means the current direction will be in the opposite direction. Okay, so it will be, the current direction will be in this or in this. The electron will be moving from source to drain, the electron current will be in opposite direction. This is your ID. The current will be flowing in this way. So we need to see like how the operation is going to be performed. So here basically the basic principle of operation in case of depletion MOSFET is, we need to apply the gate to source voltage such that it should reduce the majority carriers available into the channel. So whatever the channel is there, so this is the channel. So in the channel we are having majority electrons. Okay, so here the majority electrons are there, so we need to repel the away from the channel so that the less number of electrons should be available into this channel, and it should be reducing the current in case of depletion mode. So our motive is to deplete the channel in case of depletion mode. So we are applying the negative gate to source voltage. So here the basic operating principle is, basic operation principle is apply VGS to reduce the carrier, majority carriers of the channel. We need to reduce the majority carriers available into the channel by applying the gate to source voltage. So that's why we are applying gate to source voltage that is in negative direction. And for n channel MOSFET, for n channel MOSFET, the drain is biased in positive direction, like the drain is positively biased with respect to the source. So here we will be applying the gate to source voltage, so that is will be reducing the majority carriers in the channel, and also the drain is positively biased with respect to source side. So drain terminal is positively biased with respect to the source terminal. Okay, so to operate under the depletion mode, the gate should be applied is negative. Gate is negatively biased with respect to source. Okay, so first condition we will see here is, if we are applying gate to source voltage such that we are having gate to source voltage equals to 0. So the one is like when VGS is equals to 0. If VGS is equals to 0, at that time what will be the condition of operation? So here, as we are going to apply the gate to source voltage equals to 0. Okay, so if we are applying gate to source voltage equals to 0, then there will be no charge that will be created in this region. Okay, so on this region there will be no charge that will be created. Okay, so therefore whatever the channel is there, so at that time there will be the channel that is having the maximum number of electrons. So at that time whatever current will be flowing, that will be of maximum. Okay, so here when VGS is equals to, because when we are applying the negative gate to source voltage, the electrons will be like repelled and the electrons will be moving away from this channel. So as electrons are moving away from the channel, there will be less number of electrons to conduct current, so there will be current reduction. Okay, so if we are applying gate to source voltage that is 0, at that time there will be no charges created in the channel region. So if there is no charges created in the channel region, that means maximum number of electrons will be available for conduction. Okay, so there will be maximum number of electrons available for conduction, and also these electrons will move from source to drain. That means maximum electron will move from source to drain. So if maximum electron is moving from source to drain, it will be constituting the maximum current. Okay, so it will be constituting maximum drain to source current will be constituted, and this maximum drain to source current will be called as IDSS. So at that time when VGS is equals to 0, at that time whatever the current will be flowing, that current will be the maximum current. Okay, so this will be the maximum current. So ID will be maximum drain to source current or maximum drain to saturation current we call it, or maximum drain to source safe current. We already know the value IDSS. So IDSS will be flowing when we are applying gate to source voltage equals to 0. So the next, like, we need to increase the gate to source voltage in the negative direction. So next is when VGS is applied, that is in negative direction. Okay, so if this is the case, here the gate to source voltage is going to be a negative now. So the gate is given with a negative voltage. So as we are applying the negative voltage, therefore positive charges will be created into the channel region. Okay, so here VG applied is negative. So as we are going to apply the negative gate to source voltage into this channel region, so here we are going to apply negative, so there will be a positive charge inside this channel region. So if it is going to apply negative, positive will be attracted and negative will be repelled. That means electrons will be repelled and positive will be created. So positive will be created, that means, so here some positive charges will be created, and this charge creation will be such that on drain side it being more positive, but on the source side, on the source side we will be having larger positive charge creation with respect to the drain side, because drain side is already positively connected. So less positively charged will be here, most of the positive charge will be here. Okay, so this will be like it will be positive charge creation will be here higher, and on drain side it will be lower. So the positive charge will be created as we are going to apply the VGS in the negative direction. Okay, so this positive charge which is going to apply, therefore positive charges are created in the semiconductor or channel. So if positive charges are created, so due to this, as the channel is already having electron and some positive charges have been created, so this positive charge and electrons will be combining, so there will be electron hole pair combination recombination will be taking place, or there will be recombination now. Recombination takes place as the channel region is having both positive charges and the negative electrons. So there will be recombination taking place. So if recombination taking place means positive charges will be combining with the electrons. The positive charges combine with electron. So positive charges will be combining with the electron. So this is called recombination. So as there will be positive charges combining with electrons, so there will be reduction in electron. So there will be reduction of electron in the channel region will be taking place because of the recombination. Reduction of electron concentration in channel will be taking place. So if the electrons have been reduced into the channel region, so there will be less number of electrons, will be moving from source to drain side. So this will constitute less drain to source current. That means ID is going to reduce basically. Okay, so here the ID is going to reduce. So this ID reduction will further continue if we increase the VDS in negative direction. That means ID further reduces if gate to source voltage is given with more and negative voltage. That means we are going to increase the gate to source voltage further in negative direction, then the ID will be reducing further. Okay, so therefore there will be a time when we are going to apply the gate to source voltage in negative direction such that there will be no available electron into the channel to constitute the current. Okay, so that condition is called basically the cutoff or pinch off region, a cutoff point. Okay, so here if we are further going to increase the VGS such that if VGS that we are applying is equals to VGS off, that means that sufficient VGS to reduce the number of electrons in channel to 0 is the point that is called that VGS that reduces the number of electrons into the channel to 0, that is called VGS off. So at that point the ID will be equals to 0 because there is no electrons available into the channel to constitute the current. So that this is the point called cutoff point or the pinch off point in case of the depletion type MOS. Okay. So this analysis we can just analyze in terms of like once we are going to deal with the depletion type MOSFET, we will be plotting the characteristics. So there are two different characteristics. One is called transfer characteristics and output characteristics. Output is also called drain characteristics. So we have already seen in case of JFETs also, we used to plot transfer and output or drain characteristics. Okay, so here also we will be plotting the same. So if we plot, so the drain characteristics and the output, the transfer characteristics. So transfer characteristics will be plotted between drain current and the gate to source voltage. That means in output current with respect to the input voltage. So input voltage is a negative, so we will be plotting in 0 to negative direction. Similarly, in case of output characteristics, we will be plotting the drain current with respect to the applied output voltage, that is drain to source voltage. Okay, so this is the basic plot we will be going with. So as we come across the analysis, as we have gate to source voltage equals to 0, at that time the current is maximum, that is called IDSS current. Okay, so that was having the IDSS. As we are going to increase the gate to source voltage in negative direction, the current is going to reduce. Okay, so this current will be going to reduce, and at a point it will be like the current will be 0. So the current value will be 0. So this point will be VGS off. Okay, so this plot is basically for a constant VDS. This will be the transfer characteristic that we will be getting. Okay, in case of drain characteristics or output characteristics, as we are having constant VGS. Okay, so as we are having a constant VGS, so if initially we have taken VGS equals to 0, so when VGS is equals to 0, at that time there is like the maximum current will be flowing. But if we are increasing the VDS from 0 to some value, so it will be like initially it will be the current will be initially linearly increasing, and then it will be constant. Okay, this is the case when VGS is equals to 0. So at that time, whatever the current will be flowing, that will be ID SS, that is your maximum current, and the point at which this current will switch from a linear to a constant, this will be called your pinch off voltage. So this is your pinch off voltage. Okay, so this is VP 0, we can call it. Okay, so if we further try to increase VGS in negative direction, we are increasing the in negative direction. That means if we are going to apply the VGS in negative direction, we will be getting the curve like that. Okay, so it will be, the curve will be this. So this is like VGS is equals to minus 2 volt. Again, if another VGS is there, okay, so this will be the curve that we will be getting. And one thing we can note here is, if it is VGS is equals to minus 2 volt, the VP is equals to new VP, this is VP 1, you can call it. Another is like, if this is the case, VP is here, so VP is going to reduce as we are increasing the gate to source voltage in the negative direction further. So this is your output or drain characteristics, and this is your transfer characteristics if the depletion type N MOSFET is going to operate in depletion mode. So I hope everyone have got the point. So if you have any query, you can ask. Otherwise, we will be going forward. Okay. So we will also see how it is going to operate in the same depletion type MOSFET is going to operate in enhancement mode also. So one more point we will just note, like what is the current equation in case of the depletion mode operation of the depletion type N MOSFET. So the current equation here, current equation is given by current equation in case of depletion mode operation of depletion type and channel MOSFET. Okay, so depletion type and channel MOSFET is there and it is operating in depletion mode. At that time, the current equation is given by ID is equals to IDSS 1 minus VGS by VP to the power 2. So this is the current equation. So this is only in case of depletion mode. And here this VGS and VP is VGS and VP are of same sign. That means the VP and the VGS should be of same size to have a, like it should be of same sign. So the direction will be like if it is VGS is negative, then VP should be also be in negative only in case of the depletion mode of operation. Okay. And from the transfer characteristics, we can see the ID is going to reduce. Okay, so ID is going to reduce with respect to VGS in a parabolic fashion. Okay, like it is so following a parabolic curve with respect to the VGS. Okay, so this was the operation in case of depletion mode of operation. Next we will see is enhancement mode of operation. Okay, so this was depletion mode. Enhancement mode operation of depletion type and channel MOSFET. Okay. So we are going to have the enhancement mode operation. So similar structure we can recall from the previous. So this is your N channel depletion MOSFET, and here we will be applying the same RD will be there and it is positively biased. So this is source. The drain and source should be positively biased, and the gate terminal is now going to be biased in positive direction also. So the gate is this one, so gate to source will also be biased in such that. Okay, so this is VDS and this is VGS. So already it is having channel, and also we are going to bias it such that gate to source voltage is having the positive bias. So again here the current direction will be like this. So in case of here, the principle of operation is here applied VGS, here applied VGS must increase the majority charge carriers of the channel. So in case of depletion type of mode of operation, we were applying VGS such that the charge carriers available to the channel should be reducing. But in case of enhancement mode, we will be applying gate to source voltage such that the number of charge should be increasing into the channel region. So if the number of charge is going to increase, that means the current will be increasing. Okay, whatever gate to source voltage we are applying. Okay, so here in terms of biasing we can just see. So the biasing is like drain to source is positive, or drain terminal, just we can write drain is positively biased with respect to source, and here gate is also positively biased with respect to source. So both are positively biased with respect to source in case of enhancement mode of operation. Okay, so now we will see the case one, like when VGS is equals to 0. So when VGS is equals to 0 is there, we will see the analysis, like how the condition of the MOSFET will be there. So here it is similar to the previous one, like at VGS equals to 0, there will be no charge created. So if VGS is 0, that means there will be uh, here whatever the electrons will be available into the channel region. So this is your, so it is having predefined channel is there. So whatever we are applying VGS equals to 0, so at that time whatever the gate to source voltage, that is 0, and further we are going to increase the gate to source voltage. So whatever will be the charge available at the time when VGS is equals to 0, at that time that charge available will be the minimum charge here. Okay, because we are applying VGS positive, that means we are going to increase the charge here, but at VGS equals to 0 there will be a minimum charge. Okay, so there will be minimum electron minimum electron will be available, minimum charge will be available in channel region. Or we can just before that we can just write like when VGS equals to 0, no charge is created. So if no charge is created, that means there will be minimum electrons will be available into the channel region. So if it is minimum electrons are available into this channel region, so the minimum electron flow will take place from source to drain side. Okay, so that means there will be minimum current flowing between the drain to source side. So there will be minimum current flowing, and this minimum current will be nothing but the IDSS. So that means when VGS equals to 0, the current flowing will be IDSS only, but this IDSS will be the minimum current for the case of enhancement mode of operation. Okay, so this will be the case at VGS equals to 0. The next is like case 2, when VGS is greater than 0. So we are applying VGS that is greater than 0. So at that time when we are applying gate to source voltage, that is given with the positive voltage, that means if we are going to give the positive voltage, the negatively charged ions will be created into this channel region. Okay, so this will increase the number of negative charge, that means electrons, to this region. Okay, that means there will be more number of electrons available into this region. So more number of electrons will be moving between drain source to drain. So therefore there will be increase in current. Okay, so that increase in current will be greater than IDSS. That's why when VGS equals to 0, at that time the current IDSS is there, that is the minimum current. Okay. So when we yes, okay. So when we are going to apply the VGS that is greater than 0, then we can say okay. So when we are going to apply VGS that is greater than 0, the gate voltage is given with positive voltage. Given with positive voltage. Okay. That means if we are going to give the gate voltage positive, then the negative charges will be created inside the channel. So negative charges created in the channel. So this negative charges will be created. So this negative charges will be nothing but the electrons. Okay. So electrons will be created inside the channel. So as the electrons are created into the channel, electron concentration increases in the channel. That means more electron will be moving from source to drain. That means larger current flow between drain to source. So there will be larger current flowing between the source and drain. So if we are going to apply gate to source voltage that is greater than 0, the more current will be flowing. Okay. And this current will further increase. So ID will further increase if gate to source voltage is given with more positive voltage. So if we are applying gate to source voltage more positive, then ID will be increasing more. Okay. So with respect to that, we will again plot the characteristics. That means transfer characteristics and the output or drain characteristics. So in case of the transfer characteristics, we will be plotting the ID with respect to VGS, but in this case VGS is in positive direction. Okay, so that's why we are considering the positive side case. In case of the output characteristics, we will be having the plot of ID with respect to VDS. So this VDS is nothing positive itself. Okay, so if we plot it, it will be like, so when VGS is equals to 0, at that time there is a current flowing and that current is IDSS. IDSS. So IDSS at VGS is equals to 2, there will be IDSS current, and as we are going to increase the VGS, IDSS current is going to increase. So that increase will be the parabolic in nature. Okay, so this is going to increase with the parabolic nature. So this is the transfer characteristics in case of depletion type MOSFET, depletion type N MOSFET operating in enhancement mode. Okay, this is the transfer characteristic. Next, output drain characteristics. It will be like, so at minimum, so this is plotted at different gate to source voltages. So the minimum gate to source voltage is 0. So at minimum gate to source voltage, we are getting the plot is like, at minimum gate to source voltage it will be initially increasing with respect to increase in VDS, and then it will become constant. And this will be the case when VGS is equals to 0, and at that time the current that will be flowing is IDSS. Okay, and at that time whatever the VP is there, that will be VP0 at VP0 means at VP at gate to source voltage 0. Okay, so this is your pinch off voltage, after which the current will be constant. So this is the case when VGS is equals to 0. So suppose if VGS is equals to positive, because we are increasing to positive direction VGS. So suppose VGS is plus 2 volt. So it will be like here, and then it will become constant. So this is the case when VGS is equals to plus 2 volt. So one thing we can note here, the pinch off voltage is going to increase and ID is also going to increase. So this ID is not IDSS. IDSS will be this only when VGS is equals to 0. So this will be the new current that will be greater than the IDSS. So this current is going to increase. So ID is going to increase with respect to IDSS. Okay, as we are going to increase the VGS is equals to in positive direction. Similarly, the next one. So if we are going to further increase, so VGS we are going to increase. So it will be like this. So this is the case when VGS is equals to suppose plus 4 volt, and the new pinch off voltage for that case will be VP2. Okay, so this is the drain characteristics or output characteristics in case of depletion MOSFET, depletion type N MOSFET, but it is operating in enhancement mode. Okay, so one thing we can note is like in case of depletion mode, in depletion mode VP0 is the, so in the previous case we have seen, okay, so here VP0 is the maximum VDS or maximum pinch off. So out of different pinch off voltages, this VP0 is the maximum pinch off. So in case of depletion mode, VP0 is the maximum pinch off voltage. But in case of here, this VP0 is the minimum amongst the all. There are different pinch off voltages will be there, but the VP0 will be minimum. Okay, that means in enhancement mode operation, the VP0 is the minimum pinch off voltage. Okay, so this we can conclude from here. And also if we want to have the current equation, so the current equation is again given by ID is equals to IDSS 1 minus VGS by VP to the power 2. So this is again the same expression is there. The only difference is we can see from here is like we need to have the ID increasing as we are going to increase VGS. We are increasing the VGS in positive direction, the ID should be increasing. That means 1 minus term is there. So overall this term should be like 1 plus. Okay, so here it will be like the VGS and VP is or VGS and VP must have opposite sign. So if these two are having opposite sign, then the overall this term will be 1 plus something. Okay, because if it is opposite means VGS by VP will be negative, so negative will be positive. So overall like this term will be 1 plus something. So 1 plus something will be greater than. Okay, so it will be increasing. Okay, so that's why id will be increasing. So in case of enhancement mode, vp and vgs should be of opposite sign, but in case of depletion one, we have seen in the previous case, the current equation, this vgs and vp are of same sign. So if it is of same sign, that's why it is 1 minus something, minus will be there, so that's why the current will be decreasing from the idss. Okay, that's why it is of like both this have, both should be having same sign, but here both should be having of opposite sign, so that the id will be increasing with respect to increase in the vgs. Okay, so again here also we can see in case of transfer characteristics, id is going to increase with respect to vgs parabolically. Okay, so parabolic increase is there, and in that case also it was like parabolic decreasing current was there. So in that case we have seen there is a parabolic decrease. Okay, so this is all about your depletion type MOSFET. So we can just combine these two, just 1 minute I will be taking. So these two curves, in case of depletion and enhancement, we can combine it. So if it is transfer characteristics, okay, so if it is id is being plotted, so id can be plotted is like, so in case of depletion case, we have seen it is going to decrease is like this, or we can just have, so it was from the idss it was decreasing, okay, and going to 0, but in case of enhancement case it will be so suppose we need to plot id, this is transfer characteristics by combining both depletion and enhancement mode. So here it in enhancement mode we have seen like it is this way, but in case of depletion one it was like decreasing. So this is the point when idss will be there. So this portion will be called your depletion mode from here to here, and this is your enhancement mode. And this is your plot, this is vgs that is positive, and this is vgs in negative direction, and this is your vgs off is there, and this is 0. So this is the overall transfer characteristics of depletion type N MOSFET if it is operating in depletion and enhancement mode both. Okay, so next one is like output characteristics in both the cases.
Excuse me, sir.
Yeah, just closing it is
So
time is more. Yeah, just a minute. So id with respect to vds, this is output characteristics. Okay, so here we can just conclude is like the different gate to source voltages is going to define, so it is increasing and it is constant. So if it is vgs is equals to 0 is there, and then further if it is gate to source voltage that is going to reduce, so vgs is equals to suppose -2 is there, and the next one is like vgs that is -4 is there. So this will be basically going to explain the depletion mode operation. So in the opposite direction, in the positive case, like this will be the case when vgs is equals to suppose +2 voltage, and this is the case when +4 voltage. So by including the zero case, this will be the region will be called enhancement mode operation. Okay, so this is the overall output characteristics by including the enhancement and depletion mode operation. Okay, so this is all about depletion mode of N MOSFET operation. So similar will be in case of P channel MOSFET also, depletion type P channel MOSFET, but the only difference will be we will be changing the sign of VGS, and also the drain to source voltage that we will be having. So thank you. This is all about your depletion type MOSFET operation.